Hey everyone! Today I want to share with you one of my favorite textbook physics problems. Now this is a problem that I've seen on a Berkeley midterm and a Berkeley final. Now the reason I love this problem and the reason professors enjoy having this problem on their exams is because in one problem it tests multiple mechanics physics concepts such as gravity, normal force, friction, centripetal force, there's some fancy geometry. So it's a very versatile problem, and I think every engineer should know how to do this problem, even if it's not necessarily relevant to your work. It's a fairly accessible problem when it comes to prerequisites. If you're in high school or early college, this problem should be doable for you. And so I wanted to go over the problem and then go over the solution, and if by the end you still don't understand the problem, maybe you should go back and review. It'll be fun and it'll be good for your brain. So here's the problem statement. I have a car that is traveling on a circular shaped track at a speed of v. That's the track, that's the car, and it's going at a speed of v. And this is a top view of the track. Now let's say that the track has a radius of r, which we will need later. So here's the top view of the track. Now here's the deal. The track itself is actually tilted slightly inward towards the center of the track. So if I look at the car and the track from a side view, it would look like this. So the car on that side of the track, if I look at the car and the track from the side, you'll see that the track is tilted at an angle of theta. And so the car in this picture is going into the board. And when the car travels to the other side of the track, again, the track is tilted inward towards the center, so it would look like this from the side. Make sense? And now the car is traveling out of the board. So actually, you only need one of these pictures in order to solve the problem, but you get the concept. Now we're gonna assume that there's actually friction between the car and the track. And so we have coefficients that we will give you. We have the coefficient of static friction and coefficient of kinetic friction, which we will denote mu of s and mu of k respectively. So this is the scenario. Now the problem statement will now ask, what is the maximum and minimum speed that the car can travel in order to remain on the track? In other words, what's the maximum speed that the car can travel without flinging outward off the track? And what is the minimum speed the car can travel without sliding towards the inside of the track? And so that's the problem statement. And in order to solve for v, it must be in terms of the known variables. So the problem statement I wrote here, what is the maximum and minimum speed that the car can travel with respect to the variables mu of s, coefficient of static friction, mu of k, coefficient of kinetic friction, theta for the tilt of the track, r for the radius of the track, and I introduced m for the mass of the car, and also g for the gravitational constant. We're on Earth, so. Now solve for the maximum minimum speed in terms of these variables. I'll rewrite it on the board so it looks a little cleaner. So here I've summarized the problem again, problem statement here, and the two pictures that we care about. So how do we approach this problem in solving for maximum and minimum speed of this car on a circular track? Looking at this diagram, the thing that makes sense to do is to draw a force diagram for the car. So let's do that. Now looking at this car, what are the forces that we're going to care about? What forces exist that are pushing on this car? First of all, we have gravity, obviously. Now gravity is equal to mass times gravitational constant, mg. Because the car is on a track, there's going to be a normal force that is perpendicular to the surface of the track. I'll denote normal force as F of n. And what else do we have? Well, we also have friction force. I'm going to call it F of F. Now, what direction does friction, the force, go in? We know that friction has to be parallel to the surface of the track. So now we have two choices. Friction will either be going along the track upwards or downwards. But which way does it go? Well, it actually depends on the scenario. If we're trying to solve for the maximum speed of the car in order to remain on the track, then we know that friction must assist the car and prevent the car from flinging outwards off the track. And so which direction will friction go if the car were trying to go at maximum speed? It would go inward, because it would be pushing the car inwards towards the center of the track to go against the car's desire to fling outward off the track. So when solving for maximum speed, friction would go in this direction. Make sense? But now what about the second scenario? If we're solving for the minimum speed that the car can go on the track, in that particular scenario, if the car were going as slow as possible, then there is an intrinsic inclination for the car to slide inwards towards the center of the track. And so the friction that exists would be pushing the car in the opposite direction, away from the center of the track. And so to solve for minimum speed, the friction would go in the opposite direction, still parallel to the track. So you have the force diagrams for two different scenarios. Maximum speed, where the friction is pointed this direction, and minimum speed, where the friction force is pointing the other direction. So let's start off by solving for maximum speed case first. So I'm going to redraw things on the board so it's clearer. So now that I've cleaned up the board a little bit and drawn only the case for solving for maximum speed of the car on a circular track, what is the next step? Well, looking at the force diagram here, one step that we can take is we have force vectors going in all different sorts of directions. The next step we should take is we should take all of the force vectors and decompose them into x and y components. And down the line, you'll find why this is a necessary step for us to solve the problem. So let's do that. So gravity is already in the y direction, so there's no need to decompose it in any special way. Now what about normal force? Now, if you look at normal force, in order to decompose it into x and y components, we need to know theta, which we're given. And so, using some geometry, we will see that the angle of the normal force with respect to a vertical line is also theta. So observing that normal force is at an angle of theta away from the vertical dotted line, we notice that in order to decompose f of n into y component and x component, we would simply take f of n, the magnitude of the normal force, and multiply it by cosine of theta or sine of theta. So we involve some trigonometry in this problem. And observing this picture, we see that the x component of the normal force, or where x is this direction and y is this direction, the x component of the normal force is f of n times sine of theta, while the y component of f of n is f of n times cosine of theta. And we see that when we draw a triangle. Make sense? Alright, so let's draw those components in this force diagram down here. Alright, great. Hopefully that made sense. Now what about friction force? How do we decompose that into x and y components? Well, looking here and observing geometry, we see that the angle of the friction force with respect to a horizontal dotted line is also theta, because again, the angle of the track is theta. So let me draw a dotted line just to make it a little more clear. Alright, I had to redraw some stuff to make it a little easier to see, but this is f of f, friction force, and that angle is theta between the friction force and the horizontal dotted line. If you decompose the friction force into x and y components, by observing trigonometry, we see that the horizontal component of the friction force is f of f times cosine of theta, and the y component of the friction force in magnitude is f of f times sine of theta. We should draw that in this diagram. So here we have redrawn the force diagram to decompose all of the force vectors in the original force diagram into x and y components. Now, looking at the friction force, since the friction force is pointed downward at an angle along the track, the y component will be going down, and the x component will be going inward towards the center of the track. Make sense? Hopefully it does. So now what is the next step that we should take? We can actually write out a couple equations. First of all, we need to think about what we're trying to solve here, maximum speed. And you'll notice that we don't have any equation right now that involves the speed of the car. So how do we introduce that? Now, if you think back to your physics course when we're talking about centripetal force, there actually is an equation that you care about, and that is the following. So if I have something that is traveling in a circular motion, the net force on the object pointing towards the center of the circular path must equal to the mass of the object multiplied by the speed squared divided by r, the radius of the circular path. So this equation is perfect for what we're trying to solve for here. In this particular case, the net force on the object pointing towards the center of the track is actually the same as the net force in the x direction that is pushing on this car, keeping it in a circular track motion. So we can actually use this to write an equation for maximum speed. So let's do that. Again, the car is tilted, and the center of the track is to the right of this car. Again, this is the radius of our track, speed of a car, mass of our car, and the net f of x of what we solved here in the force diagram. Let's write out this sum here. There. We have an equation right there, and we want to solve for this maximum speed, right? Looking at these variables, we see that actually the friction force can be also written as a function of the normal force. Now, the magnitude of the friction force is by definition the magnitude of the normal force multiplied by coefficient of static friction or coefficient of kinetic friction, depending on the scenario we're talking about. Now, which one do we use? Because we have mu of k for coefficient of kinetic friction and mu of s for coefficient of static friction. Now, if you think about it, in this problem, we are solving for the maximum speed that the car can travel to remain on the track. And so we want to maximize this friction force. And we know that the maximum static friction force will always be greater than the kinetic friction. At the same time, we want the car traveling on the circular track at a constant radius. There should be no skidding up and down along the track at the angle. When we're solving for friction force as a function of normal force, we actually want to use the coefficient of static friction, mu of s. So F, that's friction, is equal to normal force times mu of s. Now, why are we given mu of k if right now we're only using mu of s? It turns out a lot of professors, when they're giving out exams and having this problem on, they will purposefully give both coefficients just to trick students and see, do you really understand the problem here and the concept here? So if we substitute this in, we have the following equation. So looking at this problem, we see that we've made pretty good progress, right? Because we're trying to solve for your maximum speed, v, as a function of a bunch of known variables. And almost every variable in this equation is known to us. We got theta, which is known, given to us. We have r, radius of the path, and m, which is mass. But the only variable we don't know is actually F of n, the normal force. So if we moved variables around and got v on one side and all the other variables in the other, we'll see that we still have this F of n that we don't know about. So how do we solve for F of n? It turns out this is a system of equations question, and we need to write a second equation. So let's go back to the force diagram. Here. Now we already used the x component of the forces in this force diagram. But what we also have is we have the forces in the y component direction. And so what can we deduce from this force diagram? Well, if the car is moving in a circular path motion, is the car flying upwards or sinking into the ground during this circular motion? No, right? And so what does that tell us about the sum of the forces in the y direction? The sum of the force components in the y direction should equal 0 because there's no acceleration of the car in the y direction, upwards or downwards, right? It's not sinking into the ground. It's not floating upwards. It's just staying at the same y level. And so we have a second equation here where we can add up all of the force components in the y direction and set it equal to a net of what? 0. So let's do that. I'm going to rewrite this because this is the equation we care about most, and I'm going to erase some of this stuff above to clean it up. And so let's sum up the forces along the y direction. We have f of n times cosine theta, and subtracting that by gravity and the friction force in the y direction. Now let's write friction force and the gravity force in terms of variables that we already determined earlier on. Alright, so now we have two equations. The first equation written due to the x component of the forces on the object. And we have a second equation here, which are the forces on the object in the y direction. And so we have two equations where the two unknown variables are v for the maximum speed and f of n for normal force. So the problem is solved now. All right, let's just crank through it real quickly. I won't bore you, let's just skip to it. So I just solved for f of n using that equation, and notice I actually made a careless mistake here. You probably caught it. F of f should actually be f of n times mu of s, and I forgot the coefficient there. So be careful. I mean, don't make a careless mistake like this. I've probably done this before. So now that we solve for f of n, and it's in variables that we already know, we can substitute this into the first equation. Sorry, the first equation. Now here you'll notice something very interesting. The m's actually cancel out. So your answer actually is not dependent on the mass of the car, which is kind of a cool result, right? So let's simplify a little more, and then we basically have the answer. Okay, so we've gone through the math, and now we have our answer. This is the maximum speed that the car can travel in order to remain on the circular track. And I won't be sloppy with terminology, we're talking about speed here. But if the professor asks you for velocity, then we're talking about speed, which is a magnitude, as well as a direction. In this case, it's on a vector around the circular track. So right now I don't have any units because the units are arbitrary, but if we're talking about speed here, then we probably need units of something like meters per second, for instance. So I was going to solve for minimum speed as well, but I figured all the steps are pretty much the same, very similar, and so I'm going to leave that as an exercise for you to do in your free time, and maybe in the future I can make another video on that case, and then we can compare answers, make sure both of us are on the right track. But here we have an answer for one of the cases. And I expect that if you take mechanics physics classes, you will likely see this problem on some sort of an exam. I've just seen on so many. I believe it's a very cool, very versatile problem. You might see maybe an easier version of it. For instance, in some cases they might have a frictionless track case, and so there you won't have this f of f term, and that might make the problem a little quicker and more fit to be put on like a 2-hour exam. So hopefully you found this problem interesting, or I refreshed your memory in some way. If you haven't taken physics before, maybe you'll see this in a crucial exam. I'm very excited about this particular problem. It's stuck with me all these years, even though I didn't see this problem since freshman year in college. So I hope you enjoyed. See you around, and have a nice day.